Alright, today we're going to be talking about vectors, so before we get started with that, let's do something a little silly. Here's a description of a vector that you might be familiar with.
Hey. I'm applying for a new film loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
So, pretty much, we have magnitude or length and the direction it's going. So, generally speaking, we will have a vector like this, starting at a point A and moving towards a point B. That would be a vector. Alright, so a lot of times when I write things out, I'll write this vector as vector U, or sometimes you'll see both top and bottom with the arrow. It just really depends on who writes it, how it's written. It's used a lot in physics. So a couple things that we'll do just to kind of get a grasp of what's going on is to add vectors geometrically. We draw the two vectors that we have, and then we connect the tail of one to the tip of the second one, and that would be the sum of the two vectors. And to scale it by a vector, so if I wanted to double vector u, I would just take the length of vector u and then multiply it. That would be doubling it. So I'm not going to have you do a lot of that graphically. I'll show you an example like that. So in this case, u plus v, and you can draw it a couple different ways, but vector u is here, vector v is going that way. I want you to notice vector u goes across one of these. Alright, and vector u, v goes this way. So really, to do u plus v, I need a straight edge. To get this correct, that would be where u plus v would go. Over here, u plus v, the v is actually like right here, so we move v to there. And then u plus v would be this vector. So do u minus v, we're going to draw v as a negative, so we'll make it into a negative, so that's negative v. And then u minus v would be this way. Alright, so like I said, I'm not going to have you really do that much with those in here. I just wanted you to see how it kind of works. What we will do is figure out the magnitude and the direction of a vector. And usually when we do that, we'll end up with component form. So the magnitude is the length. A lot of times you'll see it written down as like, looks like an absolute value of the vector. And our angle is theta. So here's the great thing. This is a lot like polar coordinates. So our component form here, we've got our direction, our u, our hypotenuse is r like it is in the polar form, that's our magnitude, and pretty much our x is going to be r cosine theta, and y is going to be r sine theta. And that'll make our lives a lot easier because we're already familiar with that. And, you know, sometimes you'll be given formulas for the magnitude of the vector. It looks pretty much like the Pythagorean theorem. And the magnitude of the vector, u equal to the square root of that. Sometimes you'll see like addition and subtraction on formulas and different things like that. It's all stuff we know how to do. It's nothing new. So here we've got a magnitude of 6 and a direction of 45. Yeah, we could draw the vector. We could do our two components. This is our x component, this is our y component. And this has a length, a magnitude of 6, and this angle is 45. If you need to draw the triangle, this one actually works okay with that. Some of them, not quite so much. It's a little bit harder to do. But in this case, we're just going to do like we did with polar coordinates. Our x component is going to be r cosine theta, our y is going to be r sine theta. And then we're just going to plug that 45 in, and the 6 in, and solve. And hey, here's the good news. 45 is on the unit circle, and we know that's the square root of 2 over 2 for both of these. And we get our x being the square root of 3 times the square root of 2, and our y is also 3 times the square root of 2. Now, when we write the vector in component form, we put these little brackets around x and y, and that tells somebody that this is a vector. You may have seen that in geometry before, so hopefully that's a little familiar. And that's our final answer there. It's a lot like a polar coordinate as far as finding the answer, except it represents something different. It represents the components of the vector. So here, we got a magnitude of 8 and a direction of 220 degrees. It's going to be a lot easier to just figure out the x component by doing the magnitude times the cosine of 220 and the magnitude times the sine of 220 than it would be to try to draw this picture out. So if you were trying to draw this picture and use a right triangle, this is where 0 is. This would be 220 degrees. And then you've got to figure out your right triangle based off of that. So it's just a little easier to just go ahead and type this in. And if you notice, 220 is not on your unit circle, so you have to type this in. And if you calculate it, you'll get approximate answers for each, which hopefully makes sense. Negative 6.13 for your x and negative 5.14 for your y component. This is going off into the third quadrant direction, so we should have both negatives. And we just finish off by writing it like it's a coordinate. Alright. So sometimes you'll have the magnitude and the direction, sometimes you won't. Sometimes you'll have the component form and you need to find the magnitude and the direction. And again, we've done all this before. So here we know our x component 6, our y component is equal to 5, and to find the magnitude, all we have to do is x squared plus y squared is our magnitude squared. So kind of like r squared, just like we did before. So, and we do 6 squared plus 5 squared, and we see that that is equal to 61. And our magnitude is the square root of 61. And that doesn't break down nicely, and we'll just go ahead and approximate it at 7.81. Now, we also did something like this with finding this angle before, when we had these x is 6, y is 5. And we said before that when we did polar coordinates that we had the tangent of theta is equal to y over x. When we were doing some of those conversions, we can use that exact same thing here for the direction. So in this case, we're going to do 5 over 6. So the tangent of theta is equal to 5 over 6. And then theta is our inverse tangent of 5 over 6. Which in this case, we want in degrees. So make sure you have your calculator on degree mode when you're working with these vectors, because we've been talking about these in degrees. 39.8 degrees. That just means from standard position, this vector is going off at an angle of 39.8 degrees. Alright, so again, some of these we have to think about a little bit more than others. This one, -2, 1, is in the second quadrant. So if we want, we can sketch this out. 0, 0 is kind of the starting point for the vector. Over 2, up 1 is the end point for the vector. So when we find our angle, we'll need to know this a little bit. When we do the magnitude, we'll just do -2 squared plus 1 squared equals the radius squared. And again, that's 4 plus 1. And r squared is equal to 5. R is the square root of 5 in this case, which we can approximate, because some of these problems, especially the work towards the end where we have some word problems, will require just a numerical answer. We could leave it as a square root of 5 and be fine with that. In this case, the tangent of theta is y over x. And when I do the inverse tangent of that, my calculator spits out a negative angle. Now, that negative angle is actually this way right here. That's the negative 25.56. I actually need the rest of that. I need to have a number that will give me an angle in the second quadrant from standard position. So in this case, I'm going to add 180 to this answer, and that will give me the right answer. So 153.4 degrees has the exact same spot. Alright? Technically it would be I need to change this to 0.6, so that makes a little more sense for you. If I round that, that helps a little bit. I must have rounded weird. You get the idea though. Hopefully. Again, -4, -6. This is in the third quadrant. So we need to know that. When we find the magnitude, we'll take -4 squared plus -6 squared. And that gives me 16 plus 36, which is 52. And my magnitude is going to be the square root of 52. Alright, so when we do this, to find my theta, the problem is going to be this. When I type this in, the negatives are going to cancel out, and I'm going to get this, or 3 over 2 even. And when I do my tangent inverse of that, I'm actually going to end up in the first quadrant with 56.3 degrees. So I'm not in the third quadrant, I'm in the first. I need to add 180, and I'll have the exact same thing. I'll have the right position though. So I'm going to take 56.3 plus 180. So my final answer is 236.3. So you have to think, am I in the right spot as far as the angle that I'm asked to find? If not, add 180 and you'll be in the right spot. Alright. Now, in component form, adding, subtracting, or scaling the vectors is a lot easier than it is to do it geometrically. So if I have the components of the vectors, all I have to do is add them together. u1 plus v1, u2 plus v2. So x plus y, x plus x, y plus y, x minus x, y minus y. Or I multiply the values by a constant. So in this one, I'm going to calculate u plus v. So vector u plus vector v is actually just going to be x plus x, 2 plus 1, and then -3 plus 5. That gives me 3, and that gives me 2. Okay. So adding them, fairly simple. Subtracting them, u minus v. I'm going to take x minus x, 2 minus 1. And then I'm going to take negative 3 minus 5. So I end up with 1, and then this is negative 8. The 2u minus 3v, a little trickier, but still not too bad. So I'm going to work on this one over here. So I like to write it like this. I've got 2 of those 2's for the u, and then I've got 3 of the 1's for the v. I've got 2 of the negative 3's for the y component of u, minus 3 of the 5's for v. So 2 times 2, and we're just going to do the math. 4 minus 3, this is negative 6 minus 15. And we get 1, and that is negative 21. So again, it's not too bad. I think if you take your time, it'll be pretty simple.